For this lesson, I'd like to introduce logarithms. To do so, in example 1, I want to consider the equations 2 to the x is equal to 4 and 2 to the x is equal to 10. So here we have a graph of 2 to the x. For this very first equation, to solve 2 to the x is equal to 4, we're asking for when does this graph take on a y value of 4? So I see there's a spot right here, and the corresponding x value is 2. So if you're looking to solve 2 to the x is equal to 4, I know that x equals 2 is the solution. And the reason is because, well, 2 squared is 4. But what about this other one? 2 to the x is equal to 10. I don't know if it'll be as easy as the one that we have here, but you can take the same approach where, okay, here's where the graph is equal to 10. It refers to this spot here. Its corresponding x value is down here. So what is that? The problem is this does not fall perfectly on an integer. So if you want the solution of this thing, I think we're going to have to try to just guess what the answer is. So to do this, in place of y1, I'm going to enter the graph 2 to the x and just try to guess what the answer is. All right, the answer looks like it's close to 3, so you could start there if you wanted to. If you type in 3, well, obviously that doesn't work. It gives you 8, but that makes sense. At 3, the graph goes up to 8. That's why you have to go a little bit past 3. So maybe I'll try, again, I'm just guessing, 3.1. I'll try that. Okay, that's closer, but it's still not good enough. That's 8.5742. All right, maybe I'll try, it doesn't look like we're going very far. Maybe 3.3? We could try that. Okay, that's better. 3.3 gives me 10.056. So that's pretty good. I mean, it's accurate to one decimal place, but 5 and 6, that's no good. Okay, maybe I could try, I'm going to make one last guess, but maybe 3.325? I don't know, I'm just making that up. That's 10.021. Okay, I mean, that's a slight improvement, but I'm already kind of like wanting to stop at this point. Like, yeah, sure, I could spend an hour adjusting these decimals until I get, 10.000, but that's a lot of effort just to solve one equation. I mean, surely there must be a faster way to do this. So at this point, all we have is an approximation, a pretty decent solution to this equation. So it turns out there is something programmed into your calculator that can help you solve equations that look like this, and that thing is called a logarithm. So just kind of quickly here, back to your calculator. On the left side, you should see the button LOG, which stands for logarithm. If you press it, you should see LOG with an open parenthesis that appears. And the logarithm itself, it's a function. It's an equation that you can plug numbers into, like, I'm just choosing this at random, but 7. If you have log 7, that just means it's some number. And in fact, the number that you get, just make sure we're getting the same thing, that's 0.845, and then it goes on for a while, but it's approximately equal to that thing. And you could type any number that you want in place of the logarithm. It either works or it doesn't, so maybe you could try, again, I'm just making this up just to get some practice with it, like what is log of 205? When I type that into my calculator, I get about 2.3117. It goes on forever as well. The takeaway here is this button is called a logarithm. It's a function that you can plug numbers into. So if you see log of a number, that is just one specific value, and its decimal approximation appears over here. So the thing about logarithms are they have a very nice property with dealing with exponential equations, and we will look at that next. So here in example 2, I have 2 to the x is equal to 10, which we have a good approximation for, but I want to try solving this equation using this idea of a logarithm. Here's the property that we're going to use. If you apply a logarithm to something, anything, to a power, the logarithm takes that power and brings it to the front of the function, and that's what appears over here. Basically, whatever is in the exponent gets removed and brought to the front of the equation, changing it from exponential to linear. So I'm going to use that idea on this equation. My first step is going to be, look at 2 to the x is equal to 10. And instead of like squaring both sides or dividing both sides by 2 or adding 3 to both sides, what I'm going to do is take the logarithm of both sides. If 2 to the x is equal to 10, well then log of 2 to the x is equal to log of 10. Now, the nice thing is, on the right side, log of 10, it's just a number that you can get from your calculator, but on this side, I have something to an exponent, and according to this property, I can take that exponent and write it in the front of the equation. So that's what I'm going to do. I'm going to take this x and write it here. So my equation becomes x times log of 2 is equal to log of 10. So just to kind of pause right here, we started with an exponential equation. I applied the logarithm to both sides, meaning these two things are still equal, but now my exponent, the variable, it's no longer there. It's here. This is now a linear equation. It's x times a number is equal to another number. Sure, like these are pretty complicated numbers, but it's extremely easy to solve this equation for x. You can just divide both sides by, in this case, log of 2. So I'm going to do that as my next step. Log of 2, even though it's very complicated looking, it is itself just a number. And I've arrived at my exact solution. X is equal to log of 10, close parentheses, divided by log of 2. And here's where you could go to your calculator and approximate the solution. I'm going to type in exactly what I have here. Log of 10, close parentheses, divide by log of 2, and then close parentheses. And the answer I get is approximately 3.321928095. This technically goes on forever, but it stops after 9 decimal places. But this is nice. This is not a very difficult process, but it gives you a very accurate solution to as many decimal places as we'll possibly need. This would be the exact solution, and then we can get this thing from our calculator. So let's try this again in a very similar type of equation where this time I want to solve for t as the variable instead of x. 5,000 times 1.04 to the t is equal to 10,000. Now I can't just simply apply this property. I can't take the logarithm of both sides because here I have 5,000 being multiplied to the thing to the exponent of t. I need to do a step first where I get rid of this 5,000. I'm going to do that by dividing both sides by 5,000. And when I do, my equation becomes 1.04 to the t is equal to 2. Okay, I can now take this brand new equation, it's something to a power of t is equal to 2, and I'm going to take the logarithm of both sides. So that's log of 1.04 to the t is equal to log of 2. This property says I can take this variable and put it in the front of my equation. It's redundant to write all these extra parentheses, so I'll just put a 1.04 within the function. And this is equal to log of 2. To solve this equation for t, I'm going to divide both sides by log of 1.04. And this is my exact solution. T is equal to log of 2 divided by log of 1.04. I can get a very good approximation by going to my calculator. And this is roughly 17 point, I'll go to 2 decimal places, 6, 7. So here's a very accurate solution to this original equation, but we didn't guess the answer. We solved an equation using this property up here and then estimated by using our calculator.